Hi, this is a video to help you through the activity on monosaccharides. Monosaccharides are sugars, and the chemical name for the class is called carbohydrates. So carbohydrates and sugars are the same thing. In front of you are 5 different carbohydrate structures and their names. All carbohydrates fit into a general formula that's shown in front of you. All carbohydrates fit into this formula of CnH2ON, or in other words, however many carbons they have the same number of oxygens and twice as many hydrogens. All of these sugars are shown in Fisher projections. Just like simple Fisher projections, any bonds that are shown horizontally are assumed to be coming out at you, and any bonds that are shown vertically are assumed to be going away from you. These are just like the simple Fisher projections that we learned about before, but we're just connecting many carbons in a row. For now, I would like you to notice that the names of these sugars have a similar suffix. They have an OSE ending, or OS. They also have similar prefix before their name, the D. This D has a meaning. It means that they are all right-handed versions of their sugars. D or L in front of the name of a sugar tells you something about the chirality or handedness. Most of the time we will be dealing with D sugars because these are the ones that are biologically relevant. All plants produce D sugars and all mammals metabolize D sugars. And once again, the OS ending just means that it's a carbohydrate or a sugar. Glyceraldehyde is a 3-carbon sugar. And you can tell that it's a sugar or a carbohydrate because it has 3 carbons, 3 oxygens, and 6 hydrogens. So it fits into the general formula for a carbohydrate. Please pause the video now and work through the first and second page as far as you can get, and unpause the video if you need some more help. First, let's review by discussing the functional groups that are present in D-glyceraldehyde. Remember, these are the things that we have in a table, so you might have even put these on your cheat sheet, or you can refer to the table that's in an activity from a couple weeks ago. The functional groups that are present in glyceraldehyde are here listed in the alcohol category and the carbonyl category. Glyceraldehyde contains an aldehyde, a secondary alcohol, and a primary alcohol. Now let's draw the Fisher projection for D-glyceraldehyde. Conveniently, it's already in the orientation so that you can just put the crosses and add the functional groups on the ends of the bonds. So this cross here represents this chiral carbon. If I want to draw a Fisher projection of L-glyceraldehyde, I can tell that this is actually the enantiomer of D-glyceraldehyde. These two molecules have the same root name, and the only difference in their name is D or L. So when I draw this Fisher projection, I'm going to draw the mirror image of the chiral carbon. It doesn't matter how I draw the other carbons because they're not chiral centers. The important parts of this is when I draw my cross that the alcohol functional group is on the left and the hydrogen is on the right. The aldehyde is on the top and the primary alcohol with its carbon is on the bottom. These are 2 representations for D and L glyceraldehyde. Notice that in D-glyceraldehyde, the alcohol is on the right, and in L-glyceraldehyde, the alcohol is on the left. D-glyceraldehyde is an aldose. This name comes from the fact that it has the aldehyde functional group. So the ald part of this name means that it has an aldehyde functional group. Later in this activity, you will learn about ketoses. Ketoses have ketone functional groups rather than aldehydes. So aldoses and ketoses are 2 types of sugars that we will talk about. The OS ending simply means it's a sugar or a carbohydrate. Now let's move on and look at longer sugars. This is a Fisher projection for D-glucose. Notice that there are 6 carbons in D-glucose. When we're numbering the carbons, we always start from the top, closest to the carbonyl functional group. In this case, it's an aldehyde. So we would call this carbon number 1, 2, 3, 4, 5, and 6. Sugars are always named D or L according to the alcohol that's attached to the chiral carbon farthest away from the carbonyl functional group. In this molecule, the carbonyl functional group is here, and the farthest chiral carbon away from this is here. Please notice that this is the 5th carbon. The 6th carbon does not matter because it's not chiral. So the 5th carbon here is what we're looking at. And we're going to look at the direction of the alcohol functional group. Notice that in this molecule, the alcohol functional group is written to the right. When the alcohol is written to the right, it is a D sugar. This is why this molecule is labeled a D glucose. It's important for you to be able to identify D and L sugars. If we're asked to draw L glucose, notice that the name here is exactly the same except for the D or L part. So L glucose is the exact mirror image of D glucose. This means that all of the chiral carbons must be drawn in an inverted way in L glucose compared to D glucose. Once again, it doesn't matter how we're drawing the carbons that are not chiral. Only the carbons that are chiral are important. Here's one representation for L glucose. Notice that all of the groups that were on the right-hand side of the chiral carbons in D glucose are written on the left-hand side of L glucose's chiral carbons. And I could say the same thing over here for the left-handed groups on D glucose and the right-handed groups on L glucose. These two things are enantiomers. They are mirror images of one another. D glucose and L glucose are enantiomers. You can tell this from their names. They are right-handed and left-handed versions of glucose. D-galactose is a special kind of stereoisomer called an epimer. An epimer is a stereoisomer that has only one chiral center inverted. D-galactose is very similar to D-glucose, except that it has only one chiral center inverted on the 4th carbon. This is carbon 1, 2, 3, and 4. Notice that carbons 2, 3, and 5 are identical in D-galactose and D-glucose. The only difference is the orientation of the groups around the 4th carbon. The definition of an epimer is a stereoisomer with only one inverted stereocenter. D-galactose is called a D sugar because the alcohol on the last chiral carbon from the carbonyl functional group is in the right-hand side. So it is right or D. The relationship between L-glucose and D-glucose is that they are stereoisomers that are mirror images. So they are enantiomers. D-glucose and D-galactose have only one chiral center inverted. So they are still stereoisomers, but they are not mirror images. These two things are called diastereomers. Diastereomers are stereoisomers that are not mirror images. So an epimer, like D-galactose, is a diastereomer, but it's a special kind of diastereomer with only one inversion of a chiral center. In the last box, I'd like you to draw a diastereomer of D-glucose that isn't an epimer. This means that you would draw something similar to D-glucose, but you would have to invert at least 2 of the chiral centers. So you could choose any 2 or any 3 of the chiral centers in D-glucose and invert them to draw the diastereomer of D-glucose. These answers will vary, and if you have questions, please post them in the comments or come see me. At this point, you should pause the video and try to work through the next 4 pages until you get to the activity on hemiacetal or ring formation. The next section of this activity is a review on alcohol functional groups and their classifications. And it asks you to identify the functional groups that are in longer sugars like glucose and galactose. Please pause the video now and complete the part of the activity that's related to classifying. Please pause the video now and complete the rest of this activity until you reach the page on ring formation. Check the key to make sure that you're correct. So far, we've only seen linear sugars. These are sugars that are written in a straight line. But sugars in solution or in your bodies will actually form rings called hemiacetals. We're going to learn how to convert a linear structure like D-allose shown here into a ring formation or a hemiacetal in a special type of structure called a Haworth projection. Sugars like to form either 5 or 6 membered rings, and for the most part, Aldoses, like D-allose, will form six-membered rings. The six-membered ring forms by forming a bond between the carbonyl carbon and an alcohol in 6 positions away from that carbon. The carbonyl carbon of a sugar is called the anomeric carbon. This is a new term. This is an anomeric carbon. It's the carbonyl carbon of a sugar. I'm going to call this carbon number 1 because it's the carbon at the end of the chain closest to the anomeric carbon. This carbon is special because it has a double bond to oxygen, and this bond is very polar. Remember, oxygen is very electronegative and carbon is not very electronegative, so this bond is polar. I can show this by showing partial charge symbols, or I could write a dipole moment arrow here. It's important to understand that this carbon is partially positive and that every oxygen on the structure is partially negative. So the carbon is going to be attracted to the partially negative oxygens on the structure. But it's particularly attracted to this oxygen because it is 6 positions away. And if these two things connect, it forms a 6-membered ring. 5 and 6-membered rings are particularly favorable, and aldoses usually form 6-membered rings. So what I'm going to do to form the ring is I'm going to connect this oxygen to this carbon. Let's redraw the structure so that we can see what happens. I'm going to tip the structure on its side, put carbon number 1 over here and kind of wrap it around to the back, and I'm going to wrap carbon 4, 5, and 6 around to the back. So I basically tipped this thing on the side and then wrapped 2 ends kind of towards the back. So carbons 2 and 3 are closest to you, and carbon 5 and 6 are very far away from you. The oxygen on carbon 5, which I've labeled as number 6, is going to connect to carbon number 1. When this forms a new bond, bonds have to break because oxygen has 2 bonds right now and carbon has 4 bonds. So once I form a new bond to carbon, a bond will have to break and a new bond will have to form. This is what it looks like. Oxygen 6 here is this oxygen. Carbon number 1 here is this carbon. This oxygen is here, and the hydrogen has transferred from this oxygen to this oxygen here. So I made a new bond between carbon number 1 and oxygen number 6. Oxygen number 6 has lost its hydrogen, and it has been transferred to the oxygen that was on carbon number 1. Now there is only a single bond between carbon 1 and its oxygen. I've drawn this in 2 different isomers. One is called a beta anomer and one is called an alpha anomer. The only difference between these 2 isomers is the orientation of the alcohol group on carbon number 1, or the orientation of the alcohol group on the anomeric carbon. Remember, this is the anomeric carbon here. Here it is again, and it's here and here. So the orientation of the alcohol on that carbon defines whether it's a beta anomer or alpha anomer. I'd like to point out at this point that every molecule that I've shown in this slide has the same molecular formula. These are all isomers of one another. These 2 are identical, they're just written in different ways. These 2 are isomers, and these ring formation or the hemiacetals are isomers of the linear form. You're going to be asked to convert linear structures into these Haworth projections and vice versa. So now let's talk about the method for converting a linear form into a ring form. If you follow these rules very carefully, they can help you learn how to draw these structures. Here's D-allose. This will be our example. The first step for converting a linear structure like this into a ring form is to first draw and number the ring positions. It's a good idea before you even start to number the positions on the linear form. Here's my ring. I draw a 6-membered ring. I put oxygen at the back right-hand corner. And then I number, starting at the very right-hand side, 1 to 6 in clockwise orientation. This is the template for any sugar that looks like this to start. So any aldose that has 6 carbons will always start looking like this. The numbers on the ring correspond to the same positions numbered on the linear form. The second thing to do is to add carbon 6. So notice that in this structure, I've only added 5 carbons and 1 oxygen. So now I'm going to add the 6th carbon and its alcohol group. This 6th carbon in a D sugar will always go onto the top position of carbon number 5. Therefore, the hydrogen on carbon number 5 will always go onto the bottom position. So you simply add these things to the top and bottom position of carbon number 5. In a D sugar, the carbon 6 always goes on the top position of carbon number 5. Hydrogen goes on the bottom. The next step is to take the groups on the right-hand side of the chiral carbons and put them on the bottom positions of carbons 2, 3, and 4. Carbon 5 has already been taken care of, and its alcohol is already part of the ring. So I'm going to add the groups on carbons 2, 3, and 4 from the right to the bottom. On this structure, all of these groups are alcohols, so I put alcohols on the bottom positions of 2, 3, and 4. The next step is to take the groups that were on the right-hand side of 2, 3, and 4 and to add them to the top positions, here, here, and here. In this case, they're all hydrogens. Now the last step is to complete the structure by adding the groups to carbon number 1. There's 2 choices, and it depends on which anomer you're trying to draw where you'll put the alcohol group. If you're trying to draw the beta anomer, you put the alcohol group on the top position and the hydrogen on the bottom. One useful thing to remember that beta anomer looks like this, is that if you put the hydrogen on the bottom, it's the beta anomer. Hydrogen on the bottom is the beta anomer. If you're trying to draw the alpha anomer, you put the hydroxyl or the alcohol group on the bottom and the hydrogen on the top. These 2 structures are identical except for the orientation of the groups around the first carbon, or the anomeric carbon. The anomeric carbon defines the anomer. Now practice with glucose and the other structures that are on your activity. Check the key to make sure you're doing this correctly. If you have comments, please post them in the comments section or come to my office or review sessions to ask for help. Thanks for watching this video on monosaccharides. If you have any questions, feel free to post them in the comments section. If you found this video helpful, don't forget to vote to let me know.